right, equilibrium note sheet 1. You already answered these in the activating strategies, but just to kind of give you a key to make sure that you are doing that correctly. So a hydrocarbon has the general formula of some amount of carbon and some amount of hydrogen reacting with oxygen to form carbon dioxide, water, and heat. So again, typical things we do is we put water on it, we blow it out, and or we use something to smother it. And there are other options, but that's what you should have. So equilibrium really looks at what are the concentrations over time of the reaction rate. So at some point they stop changing, and that's really what equilibrium is looking at, where there's no further net change. So you saw some of that in the simulations already as well. So again, understanding that kinetic molecular theory idea is that the molecules are constantly changing even though we see no net change overall. So your products are forming reactants. And equations that have an equilibrium will usually have a double arrow instead of a regular arrow. You may also see this type of arrow where it's a double-headed arrow. So there's always some type of equilibrium, but it's usually not included in equations that go mostly to completion. So we're going to look eventually at this mathematically with an equilibrium constant K. Notice the big difference between the last K we had. It's a capital K versus a lowercase k for kinetics. So that's problematic as well, but it's the ratio of the equilibrium product and reactant concentrations at a particular temperature. So again, temperature will change what those concentrations are because you know the rate of reactions change with temperature as well. And then the numerical values of K. So if you have a very small K, there's no reaction, there's very little product formed. And large negative exponents, like 10 to the negative 30th. If a large K, reactions go to completion, there's very little reactant remaining, and they can have the opposite magnitude, very large positives. And then there's the ones that are in the intermediate. So you have significant amounts of both reactants and products, and this could be plus or minus 5, and again, even some of your lower numbers like 10 to the negative 8th is still significant. So you've been looking at Le Chatelier's principle with all of the lab activities. So there are 2 separate documents. So on your worksheet online, they are there's links to both of these, so you can work on those. And then I'm going to address this back part of the note sheet. So, combustion of propane. So this is a specific hydrocarbon, so C3H8 plus O2. Again, you should be able to predict carbon dioxide and water as the products of a reaction, and things we burn give off heat. So if we go back to our firefighting measures, if we smother it, okay, we're removing oxygen. So if we're taking this oxygen out, it's going to convert this back to product. So it will quit burning because it's not forming CO2 anymore. The other thing you can do is add CO2. There are fire extinguishers that are CO2 based, so they're going to also shift that equilibrium back. When we add water to it, water does 2 things. So it removes or it adds more of this, so again shifts that there, but it also takes the heat away. So if there's less heat, that should be the one thing that shifts it up there, is so the removal of heat does violate that. So by eliminating the heat, that should shift it actually to making more product. So it's trying to make up for that change in heat. So that's the only one that's a violation. So, but again, all of those can be explained with Le Chatelier's principle. So removing product shifts it to the left. Increasing product shifts it to the left. Removing reactant also will shift it to the left. So those are your 2 big ideas there. All right, and this you saw in the equilibrium activity that you did earlier. So again, it's called the law of mass action or chemical equilibrium. For a particular system and temperature, the same equilibrium state is attained regardless of how the reaction is run. So I just picked a random number of particles. So obviously I don't have all of them here, but if this is our initial where this would be all reactant, I'm eventually going to get a mix. So these are going to be my dark ones and my white ones. Now the question is, how do I know how much to draw? So this one has an KEQ value of 0.059. So this is a small value, so there's little NO2 being produced. So I'm still going to have more reactant than I am product. So again, I know I don't have enough over here, but there will be some, whoops, that one should be of this formed, but the majority is going to be of the initial reactant. So this is a mix of reactants and products. And I'm going to draw basically the same thing. I'm going to always come back to what I started with. At the top is my equilibrium. So in this case, there's more NO2. But I am going to have some. So I'm going to put my 1 NO2 here. Okay, and this is all product. And again, the idea is I'm getting the exact same picture when I'm at equilibrium. Now, it doesn't say how long it takes, so we'd have to look at the kinetics of this reaction to see how quickly that is all going to happen. But eventually, given enough time, it will reach the same equilibrium state. Okay, so that's the big idea behind equilibrium.